Okay, hi, my name's Derek and I am your instructor for the operating systems class. Today, this is going to be kind of the first in a series of lectures about memory management. So I'm kind of planning on 3 videos. So in this first one, we're going to be looking at kind of the original, so the very first sorts of memory management systems, which were known, or at least our textbook calls these memory partitioning systems, okay? So this is mostly going to be just a kind of a straight lecture video here. We want to learn about memory partitioning in this video. So our goals are to introduce you to the reasons for memory partitioning, which was the original memory management technique, and explain, so there's really 2 flavors of partitioning, fixed and dynamic partitioning, okay? So, and I particularly though want to put this in the larger context of how it relates to modern memory management, and how modern memory management evolved from partitioning systems. So in particular, fixed partitioning is what we would call paging. So it's the idea of a paging memory system, whereas dynamic partitioning is basically a precursor of what we think of as segmentation systems, okay? So I'm going to be repeating that multiple times, all right? So this is kind of where we're going to, a roadmap, okay? So this is a table from our textbook. So partitioning refers to the original memory management. And I already mentioned modern paging evolved from fixed partitioning, and modern segmentation evolved from dynamic partitioning, okay? So we're going to look at fixed partitioning and dynamic partitioning in this video here, describe it and talk a little bit about the strengths and weaknesses, and that will set us up to understand paging and segmentation systems, all right? And then in our 3rd video, we'll look at virtual memory and how that relates to all of these, all right? So fixed partitioning is the simplest idea that you can really come up with on how to manage memory once you've come up with the idea of multi-programming. Okay, so if I need to manage multiple processes in a system, each process needs to have its own memory. Okay, so we've talked about, or you've read about previously, about the idea of protection. And that's one of the main reasons why we have processes in the system, in order to be able to set up protection mechanisms, okay? So anyway, fixed equal size partitioning is a precursor of paging. So the idea is that we just break up memory into equal fixed size partitions, all right? So in our operating system might use just one of those partitions, and so in this case, like if we have a 64 megabyte memory, so again, this is really old school, so more typical today would be something more like 64 gigabytes instead of 64 megabytes. But if we have that amount of memory, we might break it up into 8 equal sized partitions, and assuming our operating system is small enough to fit into one of those partitions, it would use the first one, and then the other 7 we could assign and run processes in them, all right? So notice, so this has some implications, okay? So this limits the process size maximum, all right? So processes have to be 8 megabytes or smaller, or else they don't really fit in a partition, all right? This also limits the number of processes, you know, so I've got 7 partitions, so I can at most be running and managing 7 processes at a time, unless I have some sort of swapping mechanism. So if I need more processes than that, I'm going to have 7 at most, and then have other processes currently swapped out or suspended, all right? So equal size partitioning, I mean, basically it's simple to implement, and that's its one and only advantage, okay? So I already mentioned some of these disadvantages. It limits the size of our programs, okay? If the program is too big to fit, you know, you're out of luck. You can't really do anything. You're not really out of luck, but then you have to really get complicated. So basically, if your program is too big and to fit into a partition in a partitioning system, you have to essentially roll your own memory management. So the programmer is going to have to do things like basically load and unload data, and maybe even load and unload code if you're really unlucky, in order to use a limited partition, all right? And main memory can be very inefficient because of what's known as internal fragmentation. Okay, so basically, if I can go back real quickly, if I have a program that's 1 megabyte or even smaller, like just a little 1 kilobyte program, it in order to use a partitioning system like this, it has to be assigned a whole partition. Okay, so if you have a very small program, it's going to be wasting a lot of that memory space. That's essentially what internal fragmentation is: wasted space due to the block of data or the program loaded being smaller than the partition. All right. So yeah, any program, regardless of its size, uses the entire partition. All right. So this is still what's known as a fixed partitioning system, but we can alleviate. We can't really solve those problems, but you can kind of alleviate both the wasted space due to internal fragmentation and the maximum program size problem by having fixed partitions, but having some varying sizes. So make a few small partitions, a few medium-sized partitions, and a few large partitions. All right. So here we've still got the same 64 megabytes of memory in this figure from our textbook, but we partition into some unequal sized partitions. So so again, now if we have a 1 megabyte program, it doesn't have if we can get it into the 2 megabyte partition, it doesn't have as much internal fragmentation. So we lessen internal fragmentation. And we can also potentially run a program up to 16 megabytes in size now because we have this large 16 megabyte partition. All right. So before I moved on, I should have mentioned, so this alleviates the problem, but it doesn't really solve. It doesn't fix error. It doesn't really fix anything ultimately. Okay, so there's still an upper limit on the largest program that I can run. So I can only have a 16 megabyte program, and I'm still going to have fragmentation, right? So when I assign programs in here, internal fragmentation. And again, if I have a very small program, there's still going to be a lot of wasted space. All right. So for a fixed partitioning system, we have to make a placement decision. Okay. So later on, so keep this in mind. So later on, we're going to be talking about, or you're going to be reading about making page placement decisions for memory management. So this is our first introduction to that concept here. Okay. So when we have equal size partitions, the placement decision is trivial. Okay. If there's a partition available, just select one of the available ones. Okay. So no partition. So given that our memory is what's known as symmetric. So given that we don't have unequal access times to memory or any other differences in the memory that we're managing the system, if all the partitions that I have available are equal, and if I've got more than one available, just select one. You can select one at random or select the first one in memory, right? If they're all occupied, then it's not a placement decision. We have to go into some sort of suspending mechanism. So we might want to pick one of the processes to kick it out of memory temporarily so that we can run the process that wants to run. All right. So for unequal size partitions, the placement decision is much more complicated. Okay, so there's two possibilities. The simplest is that we just keep one queue and assign each process to the smallest partition it will fit in, or a more complex thing is to have a single queue for each partition. Okay, so the placement decision that I just described could look something like this if you visualize it. So the simplest single queue option is on the right. So every new process you just put onto a single queue, and then when a partition becomes free, the operating system takes the next thing off the front, or when the operating system is ready to dispatch a process, takes the next one off the front, and it assigns the process to run in the partition that's the small size that the process will fit into. So if the next process I'm trying to dispatch is of size, let's say size 7, of course if 2, 4, or 6 are free, I can't assign the process to run that. They're too small for unequal size partition, fixed partitioning system here, right? So yeah, if the process is of size 7, I can fit it in one of the. If any one of these 8s is available, I fit it into there. If neither of the 8s is available, I fit it in the 12. And if the 12 isn't available, I fit it in the 16. So again, the smallest one that's a big enough size to fit the process, right? And then on the left is the more complicated. So if you have a single queue for each one, or a slight variation is if I have partitions of the same size, I might just have one queue per partition size. So I might have just one queue for the 8 megabyte partition size, right? So there, basically, any time the partition becomes free, I check on the ready queue for that partition or for that group of partitions of the same size, and I select the next process off the front to run on there. So some more disadvantages of fixed partitions. So I didn't mention these, or I did mention these. So the number of partitions that you have sets an upper limit on the number of active processes that the system can maintain at any given time. So actually, for both of the previous figures, whether it was all the partitions were the same size, or we had a couple of different size partitions, but we had broken up the system into 7 partitions. So at most, I could have 7 active processes at any given time, right? And if I have more than that, they're going to have to be suspended, you know. And the other one, though, is this internal fragmentation. Okay, so that's always a problem for a fixed partitioning system. So small jobs will waste, you know, they'll have a lot of space unused for these partitions, these fixed partitions. So the most obvious solution to internal fragmentation, to that wasted space, is to come up with the idea of, let's just use dynamically sized partitions, okay? So this is a precursor of what we're going to be calling segmentation memory management in the next video. Okay, so remember that. So this directly solves the problem of internal fragmentation. So basically, every time a new process is started, or there's a request for some new amount of memory to be allocated, we just simply allocate a block of exactly that size that's being requested. Okay. So in a dynamically sized partitioning system, partitions are a variable length instead of fixed length, and a variable number. So the number of partitions you can fit into the system is going to depend on the sizes of the ones you end up allocating. So each process is allocated exactly as much memory as it requires when it starts up. So yeah, I mean, the basic idea about this is that we only use exactly as much memory as needed, right? That's good, right? So this is, you know, again, these are both of these techniques we're talking about were the first kind of memory management techniques, all right? So let's see what happens if you use that idea to do, you know, dynamic partitioning to allocate memory for processes, all right? So, you know, we start off, so again, the same situation we had before. So your operating system needs some of the memory. So if I have 64 megabytes of memory in a dynamic partitioning system, and my operating system needs 8 megabytes of it to run, that means I've got 56 megabytes I can manage for memory and give to processes, okay? So, like if a process 1 comes along, so here notice, so another advantage, so essentially my upper limit for my process size is now 56 megabytes of memory. So whatever, so I could potentially, if I have no other processes running, could have one process up to 56 megabytes run on my system here, right? So if a 20 megabyte process runs first, so I would just allocate exactly what it needs, and then I have another process come along, allocate, it needs 14 megabytes to run, so I allocate exactly what it needs, and then I have a third process come along. So now at this point, I've only got 4 megabytes of memory available. You know, so if I have another process come along, and if it's bigger than 4 megabytes, it's going to have to wait to start running. Right? So this memory that's unused is external to any process. So this is known as external fragmentation. Okay, so and at point D in time here, you can't maybe see why external fragmentation is a problem for dynamic partitioning. But let's say then later on that process 2 either exits or gets swapped out. So now I've got a hole in memory here of 14 megabytes size and a hole in memory here of 4 megabytes in size, right? So like if process 4 starts, if it's 8 megabytes in size, I can have it run in this hole, but now I've got a 6 megabyte hole and a 4 megabyte hole, and then maybe later on I suspend process 1, so get it out of memory, and process 2, so process 2 wasn't done, it was suspended, and then we bring it back in. Okay, so now, so the problem with, to jump to the conclusion here, the problem with external fragmentation is that now I've got a couple of holes in memory, and they're all kind of small holes, right? So now if I have a process, the biggest process, new process that I can handle is going to be 6 megabyte in size. Although, I mean, potentially, if you add those up, I've actually got 16 megabytes of memory available, right? So if I could just get all these processes back together instead of having all these small holes, this external fragmentation, I could potentially still run a 16 megabyte process, right? That's not big enough to swap process 1 back in, but it is still relatively big, right? So that leads to the idea of compaction, right? So one technique, I mean, external fragmentation is bad, so the reason why dynamic partitioning ends up causing problems is as you keep running, you end up with smaller and smaller holes, usually in memory, and then at some point you don't have a big enough contiguous block to allocate for any process that wants to run right now. Okay, so in order to overcome external fragmentation, we can do compaction. All right, so periodically the operating system will shift processes so that they're contiguous. Okay, so here if we need to do compaction because no process can run or be brought into memory, I might what's known as relocate process 4 to be right after process 2. And then after I've moved process 4, relocated it, I might relocate process 3 to be right after 4. So that will get rid of these small holes and be able to end up with one big block of memory of size 16 now instead of a couple of small blocks. All right. So, but compaction, you want to avoid compaction because that's expensive. So to relocate processes, that's kind of wasted work in a sense. It's not performing useful calculations. It's overhead needed to be done by the operating system to compact things back together so that I can better manage the memory. All right. So and compaction also has this implication that we should make explicit here. So it implies the need for relocation. So I need to be able to relocate a program. So if I initially start running process 4 here in memory, if I want to relocate it, I need to be able to move it in memory, and it still needs to work, even though it's now going to be in a different location in memory. And that's not a straightforward thing. You have to set up some mechanisms to be able to allow for relocation that we'll talk about here. Okay. But before we talk about that, let's talk about placement for dynamic partitioning. Okay, so the placement decision for dynamic partitioning is actually very important because we want to avoid memory compaction. Okay, so by making placement decisions in a smart way, we can actually reduce. You can't completely avoid the need for compaction, but we can maybe put it off, reduce the frequency of it or the necessity of it for some time period. All right. So here's some examples. These aren't the only examples of placement decisions, placement algorithms you can make for the placement decision, but we'll look at these that our textbook looks at: best fit, first fit, and next fit. All right. So let's say again, this is straight off the example from the textbook. Let's say memory looks like this. So programs have been running for a while. I can't remember. So if you add all these up, you can find out how big memory is here. Actually, you can't, because you need to know what the size is of these. So the gray blocks represent processes or memory that's currently allocated, and the white ones are free blocks. Okay, so typically for a dynamic partitioning system, we have to keep like probably a list. So most likely we would have a linked list of the free blocks in memory. So this block, and often in original, so in the old operating systems, it would be an actual link, so there would be a link here to the next free block, and it would just maintain these in order to decide which free block, to search these to figure out which one is going to allocate next. Okay. And our last allocated block was this one, so that will be needed for the next fit algorithm. All right. So let's say that the next process that wants to run is 16 megabytes in size. So to run it, we need to allocate a 16 block of memory off of our free block list for this process. All right. So next fit you would just start at if the linked list starts at the first block in memory, you would start searching, sorry, first fit. So first fit basically, so you can't run a program in a block that's too small for it. So if you're doing first fit, and if they're linked from first to second to third to fourth, so on, you have to do a search. So that's why first fit is O. Well, I'll come back to it when I talk about best fit. Okay, so for first fit, I just search until I find one that's big enough in size, right? So for a 16 megabyte process, 8 megs is too small. I can't fit in there. 12 megs is too small. I can't fit in that one. But when I get to 22 megabyte, that's big enough for a 16 megabyte process. So I would take the first 16 of the 22 megabytes, allocate it for first fit, and I would end up with a 6 megabyte hole. All right. So next fit works in basically the same way as first fit, but I just start my search from the last place where I allocated. So to do like a next fit, I would probably keep my list as a circular list. So the last one in memory would then have a link back to the first one, and then I would just remember the place where I want to start the next time I need to allocate a block. So if I had a 16 megabyte request and my last one was allocated here, I would start searching from here, and 8 megabytes is too small, and 16 megabytes is too small, 14 megabytes is too small, so I would end up allocating at the 36 megabyte one, a 16 megabyte block. Now, first fit works a little bit differently from the other two. Okay, so for first fit, I have to do an exhaustive search. So that's why first fit is ON, because for first fit, I have to check every block, and it doesn't matter where you start. So I have to, for best fit, was I saying first fit? I meant best fit. So for best fit, I have to check every block. So it's ON, where N is the number of free blocks that I currently have. And I want to select the one that's closest in size to my request. Okay, so on first, when you first hear the name, it might sound like best fit should be your best performer, right? Because I'm selecting, it has best in the name after all, right? So anyway, best fit, where it doesn't matter where you start. I'm just going to I'm going to select the free block that's closest in size but is not too small. So again, you can't select things that are too small, so I'm not going to be considering the 8 or the 12 or the 6 megabyte size one. So among the ones that are big enough, I could select either the 22 or the 18 or the 36 are my candidates. And among those, the 18 is the closest in size, so I'd end up selecting that one for best fit. And notice that leaves a 2 megabyte hole, okay? So if you're on the ball, if you're thinking ahead, basically the reason why external fragmentation is a problem is when you end up with small holes, none of them are going to be suitable, all right? So that's kind of jumping to answering the question here. So which gives the best performance for this placement algorithm for dynamic partitioning? So first of all, to get the answer to that, you first have to know how do we measure performance, okay? In this case, we measure performance by, we want to reduce the need for compaction for dynamic partitioning systems. And so then that asks the question, how do you reduce the need for compaction? Well, it turns out that the best way to reduce the need for compaction is to try and keep from having lots of small holes in memory, right? So if you just have big holes instead of small holes, you'll have better choices when you do need to allocate some more memory, right? And you'll keep from having lots of really small holes where none of them are big enough to fulfill the next memory request, all right? So if you understand that, that ends up leading to the conclusion that best fit is actually the worst performer because it leads most quickly to having small holes in memory, of which none are going to be usable for new allocation requests, okay? So it turns out the first fit is, if you look at simulations, is a slightly better performer than next fit, although the reasons are subtle, and they both kind of work about the same way. So really the differences really aren't that significant. So first fit and next fit give you about the same performance in terms of keeping compaction to a minimum, okay? And in fact, actually worst fit is a good thing to explore for a placement algorithm, because if you pick the biggest hole, basically, so another name for worst fit would be just whatever the biggest hole is, always select that for the next memory request, right? Unless the only other thing that you might want to consider, if you have a hole that's exactly of the right size that you need, which would be unlikely for real systems, but if you have a hole exactly of the right size, then you would want to use that. Otherwise, you might want to use the biggest hole that you have in order to keep your external fragmentation to having big chunks. All right. Okay, so as I kind of promised as I was talking about things, so one other topic on that's really it for partitioning. Okay, so that's fixed and dynamic partitioning. Make certain you understand the difference between those. Okay, so now I do want to just spend just 2 more minutes on relocation and memory addressing. Okay, so we just noted that compaction implies that programs have to be relocatable in memory in order to support dynamic partitioning, or at least in order to support compaction for dynamic partitioning, which is really a necessity, right? So in order to be able to perform memory management, the operating system needs to support relocation. And look, relocation doesn't come automatically. You have to put mechanisms into the operating system, and actually you have to have mechanisms in the hardware level to support relocation, all right? So to support basic relocation, you have to understand what's known as relative addressing, and hardware needs to support some sorts of relative addressing mechanisms, all right? So to solve relocation, we make a distinction between logical, relative, and physical addresses, all right? So yeah, we already noted that for dynamic partitioning, it's kind of essential that you support relocation, because we can't do compaction without being able to relocate programs. But even so, even for fixed partitioning, if you want to support some sort of swapping mechanism, you also have to support relocation, because a swapping mechanism is not going to be useful if you are required to always swap back into the same location in memory. Okay, it would be possible for like a fixed partitioning scheme to swap out and always swap back in to the same partition, but that would really limit the usefulness of your memory management, okay? And it's impossible to do that for like dynamic partitioning. So once you swap something out, it's going to be hard to get that same location in memory to be a whole again, so you can swap back in, right? So for swapping for dynamic partitioning, you really have to support relocation, right? All right, so some definitions. The physical address, this goes by a couple of different names. It's known as the absolute address, or the real address. So this is the actual location in main memory of something. So all addressing schemes ultimately have to resolve down to the real physical absolute address at some point to perform the memory access. Okay, but to support relocation and later on to support virtual memory, we're going to support some sort of logical addressing schemes. So in a logical address space, a reference to a memory location is independent of where it actually physically is. Okay, so it's independent of its current assignment in memory. So there has to be some sort of a translation mechanism where we translate from our logical address or the logical address space to the actual physical address that translates to. All right, and that always has to happen at some point when we're doing when we have a logical addressing scheme. All right, and a relative. So the first logical addressing scheme that we're going to look at is known as relative addressing here. So this is a type of logical addressing scheme where the address is expressed as a location relative to some known point in memory. Okay, so all addresses in relative addressing are just relative to a base address. Right, and as we'll see in the next slide, this is supported by hardware in order to make it possible to do the address translation in a manner that doesn't affect performance too much, to make it feasible to do relative addressing at runtime, basically. All right, so relative addressing works like this, and we need to have support at the CPU to do relative addressing. Right, so basically in your program, all memory references are going to be relative to the start of the program. Okay, so if I need to access the data at the very first byte of my program, I will reference a memory address 0. Okay, and if I need to reference the program that's the instruction or the data that's 10 bytes away from the start of my program, I will just write it in my program as memory address 10. Okay, so then, so all memory references in programs are relative to 0. All right. So then, basically, when I load my program into memory, it's not going to be loaded at memory address 0. It's going to be loaded somewhere in memory, different than 0. So the start of my program won't be at 0, at the first location in RAM. So then there's going to be a base address, base register in the CPU, so that when the operating system loads my program, or wants to run my program, it's going to set this register in my CPU of what the base address is for the program that's currently running. So if my program was loaded at location 1000 in memory, the base register will be 1000. All right, and often there's also a bound register. So if my program is 1000 bytes in size, I will set the bound register that it starts at memory location 1000 and it ends at memory location 2000. All right. So then, if I have a reference, so if I want to reference if I want to get the data, say at location 10 in my relative address, every memory reference will be dynamically resolved by the CPU. Okay, so memory the relative address 0 will you'll take the base address and you will add in the relative address, say relative address 10. So if I'm currently at memory location 1000, it will take 1000, add that to my relative address 10 to come up with the absolute address. So that should end up being the real address. So if I was loaded at address 1000, if I want my relative address 10, that will be at absolute address 1010 in memory. Right? Right. And again, that happens for every memory reference. So the CPU at runtime will be doing that translation of the relative address to the absolute address. Okay. And then finally, before I move on from the slide, so usually we also do some memory bounds checking to make certain you don't do illegal access. So I will check that absolute address and make certain that it's not beyond the bounds of my legal addresses for my program. If it is, an interrupt will happen. So, and then instead of allowing the program to try and read or write memory that it doesn't own, an interrupt will occur. The operating system will regain control and will probably abort that program to do something. All right. So anyway, back to memory relocation. So how does that help? So it basically helps because if I want to, like, say, swap a program out and move it back in, or if I want to compact the program and move it, the only thing I have to do, so all addresses are just relative to the base address, or to 0, right? So if I want to move it to a new location, the only thing I have to do is just update the base register, and everything else will be the same, and the CPU is doing this calculation dynamically for every memory reference, right? So to relocate a program, I just go ahead and, I still have to do all of the hard work of, I have to copy every instruction, every bit of data from the old location to the new location to relocate it. Once I've done that, I just have to have my new updated base register, and it will be able to keep running at its new location with no modification to the instructions or the data. All right. Okay. So that's it for relocation, and also it for partitioning memory systems. So I hope that was useful information. You should keep that in mind, because then we're going to be building on that in the next video when we talk about paging and segmentation systems.